Alright, welcome. In this video I want to talk a little bit about the field of evolutionary robotics. To get started, I want to introduce you to a researcher, Valentino Breitenberg, who was an Italian neuroscientist and cyberneticist. Cyberneticist, that sounds really cool, like he makes cyborgs or something. But really what that means is that he was involved in the design of control systems, the kinds of things that you might put in machinery or simple robots. And so one of his sort of famous thought experiments involves what's called a Breitenberg vehicle, which he introduces in this work that he has here called Vehicles. And I want to introduce you to this one simple idea that he creates here. So he imagines that we have these sort of theoretical robots that are now commonly called Breitenberg vehicles, where each of the vehicles, well, there's more than one way you can wire it up, but the vehicles have light sensors on the front, and then they also have two wheels that they can control, and these are usually called differential drive wheels, meaning that you can send different amounts of power to each of them, and so one might spin faster than the other, or one might spin backwards, and so on. There's different ways you can set that up. But the way that Breitenberg imagines these vehicles is that you're going to attach your light sensor to one of the wheels. So the idea is that the intensity of the light that ends up triggering this sensor will then immediately be passed into the wheel. So the more intense light you have on the sensor, the faster the wheel will turn, and vice versa. The lower the intensity, the slower the wheel will turn. And so he imagines just building a couple of these simple robots, and he considers two possible ways of wiring them up. So for instance, in this first wiring labeled A here, we have the right light sensor is connected to the right wheel, and the left light sensor is connected to the left wheel. And then the alternate case is just crossing them over. Right goes to left and left goes to right. And he suggests that if we have these two different wirings and we place a light source in the environment of these robots, then these two robots are going to do two different things, and we can, in our own thought experiment, make sure that this makes sense. So in this, robot A here is going to get more intense light from its right sensor than its left sensor. That means the right wheel is going to spin faster than the left wheel. You can think of that as the right wheel traveling further than the left wheel, and that's going to cause the robot to turn to the left, as the diagram indicates here. More intensity on the right wheel will cause it to turn away from the light. If we cross them over instead, so now the more intensity is coming from the left sensor but is still driving the right wheel, and the lower intensity is crossed over to the left, then we're going to again have us turning towards the light in this case, still turning to the left because we're on the other side now, but we'll be turning towards the light. And so the interesting idea behind this thought experiment is that now imagine we put covers on the robot so we can't see the wiring inside, or they are a black box as we like to call it, so we don't know what's actually happening inside. And instead, we put ourselves in the position of a psychologist. We adopt the intentional stance, as we talked about in a previous video from Daniel Dennett, meaning we want to treat this as some kind of an agent. We want to understand its behavior from an agent perspective. And so when we do that, we try and interpret these behaviors, not knowing how they're wired up on the inside. We would commonly say, so here to an external observer, we might say that one of them is fearful of the light, so robot A turns away from the light and tries to avoid it, whereas the other one, robot B, tries to seek it out, maybe thinks of it as something beneficial or a food source or something like that. And one of the takeaways we can get from this is that the same tools we use to make hypotheses about the inner processes of animals or other humans even, we can use to also make hypotheses about the inner processes of a robot. So we might attribute to these robots, emotions like fear or desire, even though we know that the wiring inside the robots is incredibly simple. And one of the things we want to tease out here is that our explanations on the psychological level might be independent of our explanations on a lower level, like a physical level here, describing how wires are connected. In the same way that our descriptions of our own behaviors, when we describe human behaviors as having desires or emotions and so on, we can never look inside a brain and find desires, emotions, and so on. All we ever see are neurons and firings, and just like when we look inside this robot, all we're ever going to see are wires. We're never going to see fear or desire. That doesn't mean that fear or desire is not part of that system in some sense, some higher level abstract psychological sense. So this is one of the ideas behind this, and of course this was an idea that Valentino Breitenberg introduced quite a while ago. You know, he certainly wasn't doing this in 2023. He passed away, unfortunately, in 2011. But now we have some pretty impressive robots, including this little simple Epoch robot that is very popular in research and education purposes, because they're simple, they're small, they're lightweight, and they're open source. So it's really easy to work with them, and they're intended for this purpose. So we can take a look at one here. They're very small, actually. They're only a couple inches large. So this picture maybe makes it look a little bit bigger than it is. These robots, like the Breitenberg vehicle, are going to be differential drive robots, meaning they have these two wheels connected to motors, and they can spin forward or backwards, given if you give them different power settings. And they can also spin at different speeds, so you can turn. So this gives them a lot of freedom of movement. With the two wheels, they can move in any direction they want, turn around, spin on the spot, do kinds of different things. In addition, we have them equipped with a bunch of different sensors and actuators, not just the wheels, but in particular, there are infrared sensors, which are usually very simple, easy to build sensors that are used for proximity, so you can detect how close you are to a wall or another object. It works by shooting out just a small little infrared laser, and that bounces back, and it measures the intensity of light bounced back. Higher intensity usually indicates that there's an object that's closer by. And of course, infrared lasers or infrared sensors are like I said, fairly inexpensive and cheap to build, but they're also not going to give you the highest fidelity of information. They're good for detecting objects and so on, but they're not great at detecting much else. So you might want to have other sensors in there. The original Breitenberg vehicles, the idea was that they had light sensors. So there are light sensors on here that can sense the intensity of light impinging on that sensor. And then there's also a more sophisticated actual camera. So if you want to take actual video, so the infrared sensors can detect, proximity, but the video can detect a whole range of other things, maybe what the object is, what its type is, or maybe even just simpler properties like what color it is, things like that. So that things that the robot might use to identify the object more than just where it is. And then there are a couple other sensors here. So there's an accelerometer that helps the robot localize itself. There's a major challenge when you move from a software environment to a hardware environment, which is you move from simulated physics to real physics. And often in simulated physics, we abstract away a lot of things that maybe are problematic for us. For instance, one of them might be friction or slippage of the wheels. We probably don't build that into our model, but then as soon as you get into the real physical world, that's a very real possibility. And an accelerometer is a way to help judge where you might be relative to your own motion. So this is something that, again, we don't often build into the software models, but we definitely can build into the hardware models to help the robots, respond to things in their environment. These can also be used as bump sensors, so there are often little bump sensors. So of course, you might want to use your infrared sensors to detect proximity, but you can also detect if you actually bumped into something. There's a microphone for detecting sound. These robots they have speakers on them, so they can emit sounds. So this allows for our epochs to communicate with one another with a connection of their sensors and their actuators. And to put that into more, we can do this in other dimensions as well, not just sound. The light sensors can also pick up the LEDs that are attached to a lot of epochs. So the epochs Normally in my simulations, I usually only think of actuators as the motors that allow the Epoch to move around, but there are other things that can be used for communications, like LEDs and speakers and so on, that will emit sounds or light that other robots can pick up. The last one that I have on my list here is also motor feedback, and that's also, like the accelerometer, a great way for the robot to get feedback from its own actuators, its wheels, and so on, to let it know what it's doing, so that it can use that in its calculations to maybe determine where it is or where it needs to go. So these really simple Epoch robots are very popular in the field of evolutionary robots, especially when you want to do the experiments in physical hardware as opposed to simulation, which is also common. So this brings us to the idea that with these little robots that we can use, we want to design some kind of controller. So as it says here, Evolutionary Robotics uses evolutionary algorithms to design robots and their controllers. Well, when we're working with the Epoch robot, we're specifically talking about the controllers of the robot. And what is a controller? Well, that's like the brain. That's the software that goes inside the robot that decides what it does. And so how do we do that, or how are we going to empower the robot's brain? Well, there's a whole bunch of ways in robotics that you can build a controller for a robotic, but in evolutionary robotics, the tool that we typically use are evolutionary algorithms, and so therefore we need something to evolve. And evolving programs is a little bit difficult. It's something we can do, but evolving programs themselves is challenging. That's an area called genetic algorithms. But in evolutionary algorithms, we usually aren't evolving a program directly. We're evolving some aspect of that program. And in evolutionary robotics, it's common to evolve a neural network. So we've been talking about evolving neural networks. And so it's very common for us to use neural networks as controllers in evolutionary robotics. Now, the Epoch robots have a fixed robot design, so we aren't using evolutionary algorithms to design those robots, but it's also common in evolutionary robotics to, at the same time as you're evolving the controllers, the brains, you're also evolving the body, the shape of the body, its limbs, how the joints go together, muscles, and so on. We're still kind of in an early stage of that, but there's this really fun area of evolutionary robotics called soft robotics, where we also are evolving the bodies, and we have even got some simple ways of moving this into the physical realm, evolving them in software as physical bodies, and then building those physical bodies with 3D printers and so on in the real world to test them out with real physics as opposed to the simulated physics, as I mentioned. So this is also very common, using evolutionary algorithms to design robots. It's just more challenging. And so the more common thing you're going to find is just evolving controllers in a fixed robot. So for instance, here's maybe a very simple example, overly simplified just to make my diagram a little bit easier and tidier to view. But let's imagine that we've got an Epoch controller neural network. So we've got a neural network. Here I have built just a simple one. And we can imagine, to start out, that the output layer, these two output neurons, are connected to our left and our right wheel for our robot. And then our input layer, I've only got 3 input neurons indicated here. Again, just for simplicity, it's very common that we're going to have considerably more input neurons. But let's imagine that maybe our robot has 3 infrared sensors, and that's it. Usually, again, maybe we would have more. 3 is very limited visual abilities. But let's just assume for simplicity we only have 3 input neurons. Each one is an infrared laser, infrared sensor that is detecting the intensity of light impacted on that sensor, or infrared light impacted on that sensor. And that measurement is going to come into the input neuron and then be passed out to all of these hidden neurons as is. So we usually normalize the infrared sensor in some way so that its input, if it wasn't originally coming between 0 and 1, we normalize it so that it's between 0 and 1, and then we push that into the neuron and use that as our signal moving out. So we can imagine each of these as taking in signals from our infrared sensors. The hidden neurons, well, that's where the evolution is going to take place on the weights on these connections and the weights outgoing from our hidden neurons as well. In this simple model, I've elected to have just a single hidden layer, but you could have more than one hidden layer if you wanted as well. And then we can employ our evolution of neural networks, like we explored in our last video, to adopt the weights of our network as we go through generations. Now, one thing that's important about this kind of evolutionary robotics, and this was very popular maybe 20 to 30 years ago, this was sort of the standard way of doing this. We might pre-design a topology for our network. So we might decide usually the input layer and the output layer is given to us. How many sensors do we have? 3. Okay. How many wheels do we have? 2. Okay. So that's how many neurons we have in those 2 layers. But then the number of neurons that we put in the hidden layer is up to us. We get to decide. And we also get to decide how it is wired up. So usually in the beginning of our experiment, we might decide, okay, for this experiment, I'm going to use 5 hidden neurons, and I'm going to use, this example is what's called a fully connected network, which is very common in these multi-layer hidden layer networks, where each layer is fully connected to the next. So this neuron has a connection to every single neuron in the next layer. Now it's possible, and it's common in some of these experiments, where we might decide that topology isn't the one that we like. Maybe fully connected isn't really good. We might make this first neuron only be connected to the first 3, the second one to the middle 3, and the third one to the last 3. And if we start, fiddling around with our wirings like that, and we start grouping them up in that way, we're taking our first baby steps towards building different kinds of neural nets, like a convolutional neural net that I'll talk about in a future video. But for now, the simplest kind of evolutionary robotic neural nets are these kind where we have a fixed topology. The topology is for all of the networks in our experiment will be the same, but all that's changing for those networks are the weights of the connections between our neurons. And again, this type of evolution was actually pretty powerful. It has its limitations, but we were capable of evolving robots to do some simple tasks. They struggled with some more complicated tasks, and for that reason we needed to upgrade our algorithms related to our evolutionary algorithms related to evolutionary robotics, and I'll talk more about that in our next video. I just want to leave you with one sort of simple example, and this is based on a simulation that was created by a handful of my students. It's one that we are still working on, but what I've got depicted here is a software version of the evolutionary robotics, and as I mentioned, it's common for us to use to do evolutionary robotics in software prior to moving to hardware, if that is our goal. Or sometimes, especially in my lab, I don't do any hardware research, so I only do research in software, and once I'm done with the software, I just leave it at that. So we can imagine this as evolving simulated robots as opposed to physical robots. And in my little example here, we've got 2 robots here. They're actually back to back sort of right now. The sort of sun rays coming out, those are the infrared lasers that are being sent out, the simulated infrared lasers that are being sent out of each robot. They most of them you can see are orange, and that's because most of them are being cast so far that they impact on the walls of the environment. And the walls of the environment are something that the agents can detect. We don't want our agents to leave the environment, so we've made them sort of deadly walls. They're kind of like electric fences, or they're a cliff or something. So if the agents move past them, they die. And so the signal, the orange signal that they're getting in there, is telling them that what they are sensing is something dangerous, a wall. And so I've got this example sort of set up here. Our epochs here, there are going to be 13 of these rays being sent out, and we're simulating infrared sensors, but we are cheating a little bit because we're in software. So a typical infrared sensor detects the distance only, but we are also, so we've now got 2 neurons attached to each of these sensors, one that detects the distance and a second one that sends back color information. So the orange color we hand-picked to mean dangerous, and that's a signal that's very low on their neuron scale, so they're getting no firing for this one. but they are still getting a distance measurement. And then this here is a piece of food. At least this is a piece of food for this agent. This agent is a prey agent that wants to eat the stationary food, where this agent is a predator agent that wants to eat the other agent. So the prey agent can also has cast out one of its rays and has impacted this food, stationary food. Think of this as like a plant. And this agent wants to eat the plant, and so the signal it gets back, we decided is pink, which pink and orange kind of look similar to us, but in the hue space, they're actually on opposite sides of the hue space. So here we're using HSL color, and so hue determines the color, the shade of it, and it will move from sort of an orangey-ish on one side all the way around to pinkish on the other side, meeting at red right in the middle. But the values, the numerical values assigned to them, to the orange side is very small, like 0, and to the pink side is very high, like 300 and something. And since those two numbers are going to be the easiest to distinguish for our neural network, because once they're normalized, they will be a 0 or a 1 coming into our neural net, we chose to use specifically those two values to make them easily distinguishable for our agents, so that they can detect the difference between something dangerous and something they want to eat, something they want to seek out. So this is going back to our original idea about the Breitenberg vehicles. We've basically got two different kinds of sensors now, one that makes us run away and one that makes us go towards, or at least that's what we envision our robots might evolve to have, because they can detect two different color of objects. Now the other thing you'll notice is our predator object here also has cast out a ray, and it has hit this food object, but this ray is blue, not pink. The reason is this one is blue. That's right in the middle of the orange and the pink. And this one, when normalized for our agent, is actually going to probably give it a 0 signal, no signal at all. And that's intended to be a neutral signal for the predator, meaning this food is not for you, but it's also not dangerous for you. So you don't need to avoid it, and you don't need to seek it out. The curious and interesting thing about some of the experiments we've run with these particular robots is our predator robots in some runs will actually still hang out around the food, knowing that the prey, or at least this is us imposing our psychological analysis on it, but it hangs out near the prey knowing that near the food, knowing that the prey probably wants to eat that food and come by it, and that gives it its best chance to scoop up the prey. And of course this is common in normal hunting, hanging out at the watering hole to try and see if some prey might come by. And we thought this was just an interesting outcome of a couple of our experiments. And this might be an artifact of how we're evolving our particular ones. And I might tell you a little bit more about this in a future video, because these particular robots that we've created here, unlike the example I just provided with a fixed topology, these robots also are able to adjust the topology of their network as they evolve. Specifically, they're able to add neurons in or add new connections in as needed through evolutionary operations like mutation and crossover. They can grow their neural network to have more neurons. And so because of this, they are a slightly different algorithm, and we're going to spend more time in the next video talking about that. It's called the neuroevolution of augmenting topologies. So I think I'll leave it at that. Thanks a lot for watching this video, and we'll see you again in that next video.